started, everyone, so here we go. The next chapter, chapter 8, is a biggie. It's going to take a good part of 2 weeks to do. So you can tell something that takes that long is pretty big. It's also, for the same reason, I guess, it's very important. This is essentially how you prove something in statistics. So someone will come along and ask a question and say, I'd like to see if I can prove, and then the statement gets made. And we have set up a very precise process that you need to go through if you want to prove something is true. And this process is called a hypothesis test. And we are going to go through 4 different situations. Technically, we're going to go through 5. The first one is we're going to look at a hypothesis test on a single proportion. Then we're going to do a hypothesis test when you want to compare 2 proportions. The third one is we're going to do a hypothesis test when it's a single mean and the distribution is normal. And then a hypothesis test when it's a single mean, but the data is not normal, right? It's just any kind of data at all, really. And then lastly, we're going to do a hypothesis test when we compare 2 means. So a lot in this. So I'm going to go through kind of very vague generalizations on how we would do a hypothesis test for a single proportion. So imagine that someone said, or the accepted truth was that the proportion of people who are addicted to alcohol in Scotland was 3%. Let's just say that was an accepted truth. And there are social scientists who thinks that it's increased. In other words, there are now more alcoholics than there used to be. So how would you go about proving that? Well, the typical way you would do it is you'd collect information, right? You'd collect a sample. So in my story, they collect a sample. And this sample had 200 people in it. And P hat, the percentage who were alcoholics, was 9, which is 0.045. Now you could say, we think it's 3%, and your sample is clearly bigger. And you might think, well, that's it. You don't need to do any more. You've kind of proved what you're after. That doesn't count as proof. And the reason for that is, this is a random sample of 200. Couldn't I get another different random sample of 200 Scotsmen, and that could be 3%, and then another 200, and it's 2.8%, and so on. Every time you do a sample, you get a different answer, right? They vary a lot. That's what the sampling distribution was out there to do. So we have to figure out, is this significant? Is this definitely evidence to prove that it's more than? So we go through this little hit list. First thing you do is you check, are you allowed to do the test anyway? Now, they call it an NP greater than 5 and an NQ greater than 5. Actually, it should be NP greater than 10 and NQ less than 10. And NQ is just 1 minus P, and everybody here should be a hat because it's a sample. Right. So you should check, is the sample big enough? And the answer is, according to them, 9 yeses and 191 no's, so yes, it's good enough to do. Should also check in stage 1, was my sample random? For instance, if I was in Scotland and I wanted to find 200 people, would you agree it would be a bad idea for me to just wait outside a pub and ask the first 200 people who came out, are you an alcoholic? Secondly, wouldn't it be quite difficult to get people to admit that they're an alcoholic? So there's a very good chance that my data could just be corrupted because people lied to me. But let's assume that we got by all those hurdles, right? It's a good random sample and everybody told the truth and it's big enough. Then that's step one. Are the conditions for a test to be used? So the conditions are, is it a random sample? Was the sample big enough? And did we get unbiased data from it? In other words, did people tell me the truth? Then you move on to step two. Step two is what is called the hypothesis test. There are two different things. They're called H0 and H1. In a lot of textbooks, they're called H0 and HA. H0 is that the population proportion is still 3%. So whatever the status quo is, whatever people said, yeah, this is what it's always been, that's H0. Nothing has changed, it's still 3%. The alternate hypothesis, which is what this is called, put in the names, this one here is called the null hypothesis. This is the alternate hypothesis. And the alternate hypothesis is always going to be what you're hoping to prove. You might not end up proving it, but what you're hoping to prove. In this case, aren't I trying to prove that it's increased, so it's bigger? And so the null hypothesis is it's still 3%, and the alternate is that population proportion of alcoholics is now increased. It's greater than. There are three possible alternate hypotheses. So it's a side issue. Let me show you what they could be. Let's suppose that the null hypothesis is that it's 0.75, and the alternative could be that it's bigger than 0.75. That's the first situation. You could have a null hypothesis that it's equal to 0.75, and they're doing alternate, but H1's what they use in this book. You could prove that it is less than. Maybe you're trying to prove something has got smaller. And then the last version of this is that it could be 0.75, and that the alternate is that it is different. You're not quite sure if it's bigger or smaller, but it is different, and that's the not equals to. So one of these three guys is always going to be present in a hypothesis test. I'm trying to prove that it's got bigger than what it used to be. I'm trying to see if there's evidence that it's gone and become smaller than it used to be. Or I'm trying to just say it's different, right? It's changed. Now, back to our guy. In my story, we're trying to prove it's greater than. Now, step three, use your calculator, and I don't know why I rubbed that out. I guess I misspelled it or something. Using SALT or your calculator, find these guys. Well, p hat we've already just found, 9 out of 200, 0.045. The next number that you calculate is called the z-score, and the formula for the z-score is p hat take away p naught over the standard error of, p naught. Now, p hat is that guy. P naught is this fella. So this guy here is P naught. It's whatever that number is, that's P naught. And the standard error, well, you get the standard error by doing P naught 1 minus P naught all divided by n. Now, we typically will not do these questions by hand. We will typically do them by solve. But I want to show you once by hand, which is this question, how we would do that, at least to the point where we can still do it by hand. So on the calculator, I'll do a bracket. 0.045, take away 0.03, divided by the square root of the standard error, p, 1 minus p over n. So 0.03 times 0.97 divided by 200, and the answer I got is approximately 1.24. And that's called the z-score. Now, the last thing that we're going to get is called the p-value. The p-value is essentially, what's the probability that you got the sample that you got by just sheer luck, right, by sheer randomness, with the assumption that that was true. So if this was true, what's the chance that you'd get that or bigger? So it's a probability that you get a p-value, right? Sorry, p-value, a z-score, this guy, greater than 1.24. And at this point, you would have to use salt anyway. I'm going to do salt just on my own. And you won't see this, but you just trust me on it. And the chances that you get one bigger than 1.24 ends up being 0.107, roughly about 11% chance that this could have happened just by sheer luck. And that's stage 3 of the process. So in stage 3, you find p hat, which is called the point estimate. Putting in all the fancy names on them. The z-score, which is called the standardized test statistic. And the p-value is just called a p-value. It doesn't have another name. And that's stage 3 over with. And now you come to stage 4. Yes.
How did you, so I got the p-value part, but how did you get, like, so it was just the probability of the z-score is greater than 124? You did that all in the calculator?
No, I did that using salt.
Okay, okay.
So we'll show you in the next question. We're going to do the exact same question, but we're going to do it in salt.
Oh, okay. Thanks.
Right, and so you'll see where this comes from.
Okay.
So stage 4 is conclusion. In other words, is this p-value? Because it's all about the p-value. Everything ends up being, what was the p-value equal to? That's how you make your decision. And the test that we use is this. Is the p-value less than a number called alpha? And alpha is called the significance level. In every hypothesis test, right at the start, you have a significance level. And this one is a 5% level. You're allowed 1, 5, and 10, right? Can you see those numbers are kind of make sense, 1, 5, and 10? So significance level has to be quite a small number, because what we're trying to show is that the chance that you got this by luck is too small to be luck, right? So is the p-value less than the significance level? Well, we just found out the p-value was that guy. And is it less than 0.05? And you're only going to get 2 answers from that question. Yes, it is, or no, it's not. In this question here, the answer is no. Great. It's not. Right? Is the p-value, is that less than this? No, it's not. What does that mean? It means that there's not enough evidence. To reject H0. Which is just another way of saying, we haven't proved what we were after. Now, it doesn't mean that it's not true. It doesn't mean that it is true. It just means we don't have evidence one way or the other. You could say inconclusive. but we don't use that word in this situation. We just say there's not enough evidence to reject H0. Now, in another world, it might be yes. So if you imagine that this number was actually less than this guy here, right? Imagine it was 0.004. If the answer is yes, then you would say there is enough evidence to reject H0. I know it's a very lawyer-esque way of saying it. In English, what that means is, yeah, you're right. There are now more alcoholics in Scotland than there used to be. Now, if you're wondering why they do it this way, there's a good analogy in crime, right? And a trial. Can you think of this as a trial where you're trying to say, is there enough evidence to prove the guy's guilty, right? Well, when a case goes to trial, aren't there two verdicts, right? One of them is guilty, which is there's enough evidence, right? That's this one, right? You're guilty, you did it. And the other one is called not guilty, right? Now, have you noticed that not guilty means or doesn't necessarily mean that you're innocent? Isn't not guilty, if you're being lawyer-esque about it, doesn't it mean there wasn't enough evidence to prove that you did the crime, so we have to let you go? Isn't that? Because aren't there examples of people who you know did the crime, but still walked away free because there wasn't enough evidence to convict them, right? So think of that as there's a trial going on. Was there enough evidence to prove that alcoholics have increased? Nope, wasn't enough evidence here. Maybe there are more alcoholics in Scotland, but there wasn't enough evidence in the data I collected. On the other hand, if this happened, yes, there's enough evidence. And if you say, I'm rejecting that one, in the same sentence, even although you don't write it, if that one's wrong, doesn't this one have to be true then? It's either one or the other, right? You're either guilty or you're not guilty. How are we doing so far? It's a very formal way of proving something, isn't it? But the reason they do that is everybody has to do it the same way. So if someone in China wants to prove something to someone in France, right? They would say, this is my data. This is how I analyzed it. This was my null. This was my alternate. This is the significance level I used. Here is all these numbers, especially the p-value. Here is my p-value. Here is my conclusion. And people will look at your data and say, yep, you've proved to me that you've discovered a neutrino. Or, yep, you've proved to me that there's now more Chinese people who are alcoholics, or whatever it was you were trying to prove, right? This is the formal way to do it. If you ever look at a report, say in medicine, and they prove that there's statistical evidence, blah, 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 they should have right at the down at the bottom of the article a little thing like that, P or p-value. Sometimes they say p-value, which I think is a better term. And that tells me a lot. It tells me why they said there was enough evidence to prove that the new procedure works, right? Okay. So we are going to go through that same process the way you would typically do it, and that is we're going to do it with salt. So I'm going to nip over here and kind of show you the whole process from start to finish. Now, you remember inferential statistics? Same place. I'm going to do one sample proportion. We've done that before. In this case, there was what, 9 out of 200. Remember the 9 drunks in Scotland out of 200 in my sample. And I'm now going to do hypothesis test. See hypothesis test. Now, this fella here is the 0.03 guy. So this is where you put your status quo, right? Your 3%. And we want it to be greater than that. We want to prove that it's less than that, or we want to prove it's not equal to that. You see the three choices. So I want to prove it's greater than, right? That's what we're trying to show here. And hypothesis test, right? The P0 value, right? The status quo value. And I want to prove it's greater than. And I will now generate the results. Now, can you see my null hypothesis written down for me now? And can you see my Z statistic rounded off a little bit? And can you see my p-value? So all the things that you need are basically on those 4 lines. Now, the p-value I got was this number. Yep, that guy is, well, it failed, right? It wasn't less than the significance level of 5%. And that's pretty much how you do that type of question. So I'm hoping as we do enough of these, we'll be able to get comfortable in doing these questions using SOLV. So which one will I do? I'll do one to start with. Can you see question 1 on your screen right now? Okay, so a random sample of 40 binomial trials doesn't matter. That just means each trial is independent of the other and one result has no effect on the other. And it resulted in 16 successes. Test to claim that the population proportion of sexy does not equal 0.5. So the key to this is what we're trying to prove, right? Test the claim. So we're trying to prove that the population proportion, and here's the key, does not equal 0.5. Okay, so let's get these guys out of the way first. Is NP and NQ bigger than 5? 16 yeses, 24 no's. Yes, you can do it. Click on that. If you don't click on that, theoretically, you shouldn't do anything else. You should walk away from the question. So there's a pretty good reason that that's probably going to be yes. Now, in our question, one of these 4 choices is going to be the null and the alternate. Now, we are trying to prove that it's not equal to 0.5, which creates that one. The null hypothesis is it is 0.5, and we're trying to prove that it's different, not equal to 0.5. And then you've got all this stuff. So p hat goes here, z score goes there, p-value goes there. So I should be able to just, what's that? 60, 90, 40, right? Should be able to go here and do 16 out of 40. The null hypothesis goes here, and that was 0.5. And the alternate is I'm trying to show it's not equal to. And now I'm going to generate the results. Oh, and here we go. Right, there's a guy here called the Z statistic, and the guy underneath it is the p-value. So let's see what questions are asking. The standardized sample test statistic is the fancy word for our Z score. So when they ask you for the standardized sample test statistic, you're going to get the Z score, which is that guy. Into 2 decimal places, I'm going to turn them into that guy. And the p-value happens to be this guy. And it did, to how many? To 4 decimal places, so that's that guy. And p hat is, what, 60, 90, 40, so did it have that? Yeah, it did. On the screen that you can't see, p hat is 0.4, right? So I'm just reading it straight off. So you should be able to get those 3 guys from SOLV, okay? Let me show you what they look like again. Can you see the non-alternate bit? See the test statistic, the p-value, and down here is the p-hat. And the next bit you have to do, and I'm going to do it on paper, is the test part. In this particular case, they told me that the significance level is going to be that number. So here's my test. Same test every time. Is the p-value that I got, is it less than alpha? Is the 0.2059, is it less than 0.05? And the answer is no, it's not. And because it is no, it's not, we'll use their words, you'll fail to reject H0. And what does that tell us? It tells us it's inconclusive. And that's it. Now, if I had done this calculation and this guy had been a tiny number, you know, like that kind of number, wouldn't the answer be yes? And when the answer is, that's what you say when it's no. And when the answer is yes, you will say you're going to reject H0. And what does that mean? Well, it means you've proved whatever it is you were trying to prove. So you want tiny p-values. Tiny p-values is evidence that what you think is true is going to be true, right? Tiny p-values. Sounds contradictory. You might think big p-values is what I should be looking for, but it's not. Tiny p-values is what you want. Tiny p-values mean, yep, you've got the evidence you're looking for. Analogy. If you convicted someone of a crime, you know it's impossible to be 100% certain, right? But if you're 0.0001% chance that you got it wrong, isn't that enough to put somebody in jail, right? You're going to feel pretty comfortable. Do you make mistakes? Of course you do, right? There's innocent people, you know, who are in jail today. Problem is, you don't know which ones are innocent, agree? Because if you went to a jail and said, how many of you are innocent and want to get out? Wouldn't there be a large number of people said they were innocent, even when they're not, right? So there's, you know, it's hard. So the next one I'm going to do is a version of question 2. I'll give you a background from it. It's called Benford's Law. Anybody heard of it? It's very often used in finding out if someone cooked the books in accounting, right? Made up numbers, right? You know, for whatever reason, right? To try and get people to invest in their company, right? Or to try and steal money, right? Right? It's called Benford's Law. Anybody heard of it? He discovered, just by a process of looking at lots of data from banks and places that weren't cheating, that when you talk about money, a 1 in the first position. So, you know, it's $1,750, right? That kind of thing. Or it's $11.41, or it's $1.70, right? There's a 1 in the first position. He discovered that it's not random. You might think there's just as many, you know, money numbers that start with a 1 and a 2 and a 4 and a 7 and an 8 and finally a 9, or even a 0, right? Because you could have 0.12, right? 12 cents. You would think they were all equally likely, but he discovered that the one happens 0. It's in here somewhere if I go looking for it, 301 times, which is approximately 30% of all numbers to do with money. 30% of them start with a 1. Okay. So let's suppose I was looking at a company's balance sheet, and I think that it's a load of garbage. I think they just made up a whole list of numbers and plugged them in. So I collected 1,000 different entries, because you can imagine a huge multinational company. Couldn't they literally have millions of, things getting bought and things being sold, right? Could be literally millions of them. So I just took a random sample, got the computer to pick 1,000. And the percentage of them that started with a 1 was 2,991. Is that too many? That's too many. 299. In other words, 0.299. Let's make it a little bit more interesting there. 0.289. I want to see if I can get evidence. So here's our question. Is this company cooking the books, or is their data accurate? So the question becomes, if nothing suspicious is coming on, the number of data, the money that they have starting with a 1 would be that. And the alternate is that it's less than that. Oops. Right. 28.9% of their data started with a 1. 30.1% is what you'd expect if there was nothing suspicious going on. Would you agree that is slightly suspicious because it is lower? But is it that low? Couldn't it just be luck, right? Randomness? Let's find out. So a lot of what I'm doing here is just the salt part. So we go over here and we'll use salt. Here we go. And so one sample proportion. There was 289 of them out of 1,000 that started with a 1. The comparison is that if nothing suspicious was going on, it'd be that number, but we are pretty sure that it's less. We want to prove that it's less. And less means they've cooked the books. So let's generate results. The most important number is that number, isn't it? Would you agree that 0.204 is definitely not less than 5%? Okay. Different company, and we'll make this 269. Right? So a different company had 269. Let's generate results. There we go. Can you see the p-value now? Isn't that less than 5%, 0.05? That company was cheating. That company, we've got strong evidence to prove it. Now, what you could then do is a full audit, right? You're not just going to convict somebody on, a company and, people end up in jail. Aren't you going to do a full audit and figure out why? It's much easier to do a sample and this test, isn't it, than to do a full audit of every company, because that would take an awful lot of time and money. So it's a very quick, easy way to do things. I bet you the IRS do the same thing. Do you know the IRS are checking your data, all the numbers that you put in? Not the people who don't claim anything, but the ones that claim everything kind of people. I bet you they do that test on it. And if there's far too many of the numbers bigger than 1 or less than a 1, wouldn't that be, maybe we should audit that one? Kind of cool. Well, it's not kind of cool because I don't want audited.
I mean, if you were cooking the books and you knew about Benford's law, you could run the data yourself and make sure that you were within that little.
Yes, you could, couldn't you? You could, yes. So none of you end up being accountants and doing that, right? I am not telling you how to beat the system. I'm just telling you how they catch people who don't know about Bennett's law, right? Okay. So in this particular question, I've forgotten what this one was now. Right, the one we just did was Bennett's law. So let's show you around their version of Bennett's law now. Just show you how it's phrased. Benford's law, I should say. And they tell you about all the good stuff. Now, 222 entries. So I better write that down because I'm running short of room. And 48 successes. So 48 out of 222 had a 1 in them, which is what you would expect. And the significance level is 5%. Right, I'm good to go here. So going to use salt. Bring it over. After you've done 2 or 3 of these, isn't there a kind of same old, it's like the same thing, but just different numbers? So what do we know in this one? We knew that there were 48 times a 1 appeared out of a sample of 222. According to Benford's law, this should be 0.301, is it? Yeah. And we are trying to prove, what are we trying to prove? Okay, so we're after a lesson. Just checking that. Let's generate results. So there's your null hypothesis. We're trying to show that it's less. Here is your test statistic. And wow, would you look at that p-value? That's tiny. Okay. So what is the significance level? Is 0.05. Which one of these was my null and alternate? Wasn't it this one? Right? It's equal to 301, or we proved that it's less than. What sampling distribution did we use? We used the standard normal, which is going to be the answer for every one of these questions. So after you've done the first one, just use that all the time. We are assuming that the distribution is normal, which we can do. Now, the test statistic was the z-score, which you can't see, but I'm now copying, was this guy. And to 2 decimal places, you get that. The p-value that we got, which is going to be to 4 decimal places, is that guy. And then it says, do a little sketch of it. Well, if you do a little sketch of it, my picture doesn't have any, that's weird. I'm going to zoom in. Maybe I can see what's going on. Okay, there's a tiny bit of shading there. And there's a tiny bit of shade. Oh, okay, that's almost impossible. Can you trust me that there's a tiny bit of shading over to the left here, and that's where the 0.00 thing came from? That was a horrible question. I had to zoom in just to see it. And now, our answer is tiny. Doesn't that mean that we reject the null hypothesis and the data is statistically significant? And what does that mean? It means there's sufficient evidence that the guy was cooking the books, and then you read over a couple of versions of the same story. Question 3 is the same situation, different numbers. Skip by that one. Right, next one. Is the national crime rate really going down? Well, this must have been made a few years ago, because I would say that most people would say it's going up, right? But let's do it from when this particular question was being asked. Some sociologists say yes. Oh, there is a way for the crime rate to go down. Just don't make certain things a crime anymore. See, if shoplifting's not a crime, won't the shoplifting crime rate go down? And if having riots is not a crime, then the crime rate will go down. That's clever. Yeah, okay, you could do it. They say that the reason for the decline in crime rates in the 80s and 90s is demographics. Okay, so they're looking at the past. That could be true then. And it seems that the population is aging and older people commit fewer crimes. Okay, I could believe that. According to the FBI and the Justice Department, 70% of all arrests are males aged 15 to 34. Wow, that I didn't know. So 70% of all crimes are committed by guys in the age 15 to 34. Interesting. Suppose you are a sociologist in Wyoming and you take a random sample of police files and you showed that 33 arrests in the last month, 19 of them were males. So you've basically got P equals 0.70, 70%, and you've got 33 out, 19 out of 33. Use a significance level of 1%. So everything I need to know is here. You see a significance level alpha. Can you see my 19 out of 33? Right? Now, what am I trying to prove then? Test the claim that proportion of such arrests is different from 70%. So we're wanting to see if Wyoming is different than, you know, the general national, is it, right, number? Yeah. Let's find out. So hit use salt. So see that about the crime rate going down? That actually doesn't have anything to do with this story, did it? We just want to find out if in Wyoming, is it 70% or not? So let's find out. One sample proportion. We got 19 out of 33 people who were arrested in 1 month in Wyoming. Is it 70%? And we're trying to prove the right is not equal, right? It's different. And generate results. And there's my p-value. Is that p-value small enough to be evidence? 0.119. Is that a small enough p-value to be evidence that it's different? It has to be less than 1%. Is that number less than 1%? So no, I can't tell you if Wyoming's any different than the national average. Based on that, it certainly is not. It's not obvious. In fact, if you calculate the data, roughly about 58% are in that age group, which is smaller than 70, isn't it? 58% is smaller than 70, but it's such a small sample. That was just caused by randomness, right? That could happen quite easily by randomness, so it's not really evidence. And that's it. I think the next one we are going to do is this class. Right, so 2, 4, 6, 7, 8, 9, 2, 4, 6, 8, 10, good. I'm breaking all the rules here. So there's only 10 people in this sample. So each one of you is going to be 10 people. So I'm going to make it so that my sample's 100, right? Just so it can actually work. So I'm going to ask you. Oh, first, I kind of need a story. So I'm going to think that, here's my story. I believe that less than 50% of Americans went to the movies in the last week. I think it's less than 50% of you went to the movies in the last week. So H0, oh, let me do this. You can see me at setting it up, and then I'll ask you the questions. So I'm going to set up my null hypothesis is that it's 50. Oh, I know what my alternate is, that it's not 50%. So it might be more, might be less, but it's not 50, right? So it's not half of you, right? And I collected 100. So here is my sample. Here we go. You know the little reaction thing that's down here? And you go, thumbs up, right? That's you voting. And so how many have been to the movies in the last week? And I have. None of you, apart from me. Okay. Then we have our data.
What did you see?
Oh, I went and saw the Thor one.
Was it good?
It's very good. I enjoyed it. My wife didn't enjoy it quite as much, but I enjoyed it. So there's a lot of preference.
Where's it?
Was it called Love and Thunder or something? I think its title is. Yeah. Or Love and Vengeance or Vengeance and
We were
Thunder.
thinking of going and seeing that one at the drive-in.
It's fun. It's a good movie. I saw it last week.
Why am I not counting you then? You saw it in the last
I
week.
tried to put the thing in, but it didn't work.
Oh, okay. So that's even better.
Gotta
so-
sum up.
Right. We now have a p-hat of 20 people, right, out of 100. So 0.2. That's good. I need a significance level here. I'm going to be really tough. Right, I'm picking a 1%. That's the hardest hurdle to go over, right? So if it works with 1%, we can be pretty sure that we've got evidence that it's not a half. So I'm using salt. Here we go. Let's kick over and do our calculation, which you should be getting used to because it's pretty much the same calculations every time. And one sample proportion. It's now 20 people out of 100. It's not equal to half, so I can keep that. Generate results. Whoa. The p-value is so small that it's essentially negligible, right? It's trying to tell me that it's less than 0.00001. That's as good as it can calculate. Would you agree that is definitely less than nothing 0.01? And so, yep, based on our sample, I could prove that it's definitely not a half. In fact, now that I've looked at the sample, couldn't I prove it was less than a half? Instead, they just not equal to. Now, if I change that to less than a half and generated the results, you see it makes virtually no difference. It's still so small. Now, if I did the real numbers, which was only 2 out of 10, and I generate results, wow, it still was significant. Do you see it? It's 0.02. Well, not significant on the 1%, but certainly significant on the 5%. So even with a tiny sample of 10, if there's a big enough difference between the yeses and nos, I can get evidence to prove something. Although I'd be highly dubious about a sample size of 10. Okay. Next one, question 5. Women athletes at a certain university have a long-term graduation rate of 67%. So I'm writing that down. P equals 0.67. Which really just means 2 out of 3 women athletes actually graduate from the university. The opposite of that is then, doesn't that mean 1 out of 3 didn't graduate? So if you go to university and you're on a athletic scholarship, don't they expect a lot of commitment from you because they're paying your fees? So you have to turn up 4 hours a day for training. I'm making this up, but you know the kind of thing, 4 hours a day, and then you have to go to the meets and you have to do this and you have to do that. Couldn't that be such a large drain on your free time that it might affect your chances of passing? Because I know if you pay to go, the success rate should be higher than 67, unless you just drop out because it's too expensive, which unfortunately it is. Right. So in this story, in this particular university, 21 out of 36 women successfully passed. And we're wanting to show, does this indicate that the population of athletes who graduate is now even less than 67? So we think it's used to be 67, but you think it's got even worse, right? And that's what we're trying to prove. So I'm going to hit the sort button and got all the numbers I need. Significance level is 10%, so that's not that big a hurdle to cover. So for the women, 21 passed out of 36. The long-term average is 67, and we're trying to prove that it's less than that, so that's correct. And I'll generate results. And inconclusive, agreed, 0.13. That isn't proving it's got worse. And that's basically significance level then would be 0.10. We want to prove it's a less than. We always pick that one. The test statistic, which is the Z-score that you can't see, so I'm just copying and pasting it because it's insult. Was that number to 2 decimal places. The p-value was this number, and I'll round that off to 4 decimal places. And if you want to do a sketch of it, it'd be that one, right? You know, to the less hand side. And do you reject it? We fail to reject it. Not statistically significant. And then there is insufficient evidence, and you're finished. So you would be able to, well, you wouldn't actually say that, because when a social scientist does something and the answer is inconclusive, do you think they're going to write a paper and saying, we spent all this money and we asked all these people, and the conclusion is that we can't tell if there's a difference? That's like somebody telling you a news article where nothing happened, right? Who's wanting to read that, right? There's nothing happened, right? There's no evidence. So those things never get published. You only publish when something's significant, right? Oh, we found out something's changed. Then you publish. Okay, next one. Set this one up. The Department of Transport has reported that 77% of all fatal injuries in automobile drivers were intoxicated. Right, so don't drink and drive. Makes sense. 77% of fatalities. Right, now there's lots of accidents, but maybe when you're sober and have an accident, you're not traveling as fast and you're not hitting like head-on crashes, right? You're more bumping into people rather, you know, doing, that's my guess anyway. So a random sample of 50 records of automobile driver fatalities in a certain county showed that 33 were drunk. Okay, so I got that. 33 out of 50. I need that. Significance level is going to be 0.10. I got that. And we have to try and prove that it is there, that it's less than 77. So I got that as well. So significance level 0.10. It's equal to 77, so it has to be one of those two, and I'm trying to prove it's less than, so it's this one. Just pick that because it always is. And these guys here are going to come from salt. So here goes. Make that 33. Make that 50. This number here is that the right number? What is it? 77. Okay. This number is 77. It's less than 77. So, yep, less than 77. We are good. And there's my Z score, which they will call the test statistic, samples test statistic. And here is my p-value. Rounding them off to 2 decimal places and rounding this off to 4.
I have a question.
Yes.
Is it always going to be, for the sampling distribution, will it always be the standard is normal?
Yes.
Whether it's greater than or less than 5?
Yeah. Don't matter. Why is it standard normal?
Yeah.
When you do proportions, the sampling distribution is always going to be normal in shape. Standard normal is why we use it. Now, bigger than, less than, or not equal to doesn't change the sampling distribution. So
Okay.
we're going to use the standard normal in all 3 cases.
Okay.
Right.
Thanks.
In this case here, would you agree that that's less than 10%? So that would prove that this is decreased. Well, maybe that's good. That is good news, right? Because maybe advertising campaigns have got people to, stop drinking and driving, all those types of things. That's good news. I like that if that's true. And then you do the usual, which picture is it? We're doing a less than, so it's that one. If we were doing a more than, wouldn't it be this one? If we were doing a not equal to, it would be this one, and it would never be that one. And is this significant? Yes, we can reject the null. That's this one. And there is sufficient evidence as well. Are we good? Okay. So, a little pause here, continue in a moment. This is how you prove things. So, let's suppose we go out there and we look at drug usage, and we find out that the go-to drug for teenagers has changed from what it used to be to some new drug, right? So let's say it used to be ecstasy and now it's fentanyl. God, hope not, that stuff kill you slow down. But let's suppose we think it might be, it's changed. Then you can't just go by a gut feeling, don't you want to collect data? So you collect data on the drug of choice of teenagers that take drugs, right? And you somehow or other you get truthful information. If you notice that there's a change in drug usage in high school students, wouldn't that be important if you can then transfer that information to the people that need to know? So you might want to say to the people in hospitals, first responders, the kids are taking this drug now more than they used to take the other drug. So if you come with a kid and he's OD'd, the chances are he's probably taken, fentanyl now than E, right? And that might choose how you're going to treat them. Because very often, if somebody's unconscious, you don't know much else except they're unconscious, right? So how you would treat them with one drug might be totally different. Now, I don't know enough about fentanyl except to know it's really, really dangerous and people shouldn't be taking it because it'll kill you stone dead, right?
It's a heavy narcotic.
It's really strong. So it
Yeah.
basically shuts down your whole body if you take too much and you keel over and die.
Yeah.
So if you knew somebody was OD'd on fentanyl, would the druggy treatment be some kind of injection that counteracts that in some way? A
Narcan.
stimulus.
They get Narcan.
So they get Narcan. So, right, if someone OD'd on ecstasy, what would be the difference in that? Would it be the same treatment, or would you do something different?
It would be something different. So Narcan only works for like opioids and heavy narcotics.
Right. So if you didn't know anything at all, your best bet would probably, if you knew that this was a new drug of choice, to go for the fentanyl treatment rather than to go for the ecstasy treatment.
Yeah. So if we don't know, we're gonna Narcan you either way, and then see what happens.
Right. So that's your first one. If they ain't doing it, you try the next one, and then
Yeah.
things get tough because then you don't know what they've took.
Yeah.
Right. So, God, I'm old, but it's good. Don't take drugs. Bottom line, not worth it. Bad idea. Screw up your life. How many rock stars have ever said, "Gee, I'm glad I'm a drug addict. My life is so much better now"? Don't think I've heard that sentence off any of them. Strange. I got to get this out of my head. Take rock stars, right? There's a high preponderance of drug usage amongst rock stars. Would that be a reasonable assumption? Rock stars are pretty intelligent people, right? They know that taking drugs screws up their life. Yet so many of them take drugs. I've never understood that connection. Why do you take drugs if you know the bloody dangers of it? Are they just, I'm better, I can take them and leave them, I'm okay?
A lot of times they're just unhappy with their life. Like, yes, they may be a rock star and they may have a lot of money and things going for them, but there's a bunch of different, deeper things that are underweighing it. So they take the drugs to basically not feel all of the other things.
Oh, that's sad.
It's really sad.
Yeah. Well, I've never taken drugs in my life except the ones that my doctor keeps on giving me, and there's enough of them. I don't need anybody else's. Okay, let's change the topic. What's your favourite colour is the next question. Well, a large survey of countries, including United States, China and Russia and lots of other places like Kenya, they asked people their favourite colour. And I can see it in front of me. I don't think you can. Can you see the question in front of us? Ah, well, do you know it's blue? And that seems to be across cultures, right? China and America and Kenya. I mean, that's pretty different cultures, right? Yet blue seems to be the favorite color. And it's 25% or 24. And the cool thing is that blue is my favorite color. So go figure. Now, suppose you take a random sample of 55 students at our college. And 11 of them said that blue is their favorite color. So, okay. And we're going to do a significance level of 5%, 0.05. And we're going to check this time, does this information imply that the color preference of all is different, right? So just different. So everything I need to know should be here. Let's put it in. So it's going to be 11 out of 55. And we know that, was it 24? Yeah. We know that it typically should be 24, but we're going to see if this data is evidence that it's different, right? Different means not equal to, and generate results. Would you agree that that's a horrible p-value for proving anything? 0.48, unless I've screwed up somewhere. No, don't think I have. That's very insignificant, right? So, whatever. Let's pretend that it was 22 students who said blue. Ah, do you see that is significant? If that had been my sample, I would say, yeah, that's evidence that, at least for this subgroup of the human race, their preference for blue is much stronger. And all the usual numbers and questions, you see it's very much same old each time they ask you same types of things. Here's a general knowledge question for you. In Western cultures, isn't black the color of funerals and mourning? What color is it in Asian countries?
Is that red?
Interesting. I didn't know that. I'm asking. It's red.
That's a guess.
Anybody know for sure? I know it's different, but I didn't know it was red. I'm not saying it's not red or it is red.
I think it's white in some countries as well.
White's the one I was thinking about. I wasn't sure if that was Asian. That could be, Muslim countries. That could be white. No, I don't know. But certain colors are different in each society, right? Certain colors mean, for instance, if you're going to get married in Western cultures, and probably a lot of the Eastern ones as well now because they've picked up, don't you tend to get married in white of some kind? At least that's the usual cultural norm. But I'll make this up. Maybe in Tibet, when you get married, you dress in yellow. Maybe yellow is the marriage color. Right? So cultures have different color choices. And I drifted, as I frequently do. Let's move on to, I want to get this thing finished, so that's my kind of goal anyway. Let's move on to the next question then. And this set of data is to do with, came from a book, The Wolf in the Southwest. Southwest is California, right? That's Southwest. Yeah, mostly California, right? So in this book, the guy, David E. Brown, from the University of Arizona, so maybe Arizona is also part of the Southwest. Before 1918, the proportion of female wolves in the general population of all Southwest wolves was about 50%. Okay. So if you found a wolf pack, half would be males, right? Half would be females, right? Seems reasonable. However, after 1918, Southwestern cattle ranchers began a widespread effort to basically kill them all off. And in a recent sample of 37 wolves, there's only 11 females. One theory is that the male wolves tend to return sooner than the females to their old territories. Okay. Does this data indicate that the proportion of females is now less than 50%? So I've got a significance level of 1%, and I'm trying to prove that it's less than, in this case, 50%. So everything that we need was in that story. So there was 11 females out of the 37 that they caught. Is it 50%? Or can we prove that it is less than 50? And then we'll generate results. And that's the key number for the decision. 0.2068, isn't that definitely less than 0.01? So that is evidence that there is less females in the wolves of Southwest America right now. So yeah, less females, more males. Fishing lodge, nah, pretty standard. Ugh, I don't like the looks of that one, it's hard to say it. Oh, I've only got time, so I guess. What do you want? Do you want prose rhythm question? Or do you want me to do the fishing lodge question? Any preference?
Fishing lodge.
Yeah, I don't like that word one. In a fishing lodge brochure, the lodge advertises that 75% of its guests catch a northern pike that's over 20 pounds. So in other words, come here and there's a 75% chance you're going to get a big fish. Okay, so I know that H naught is that P is 0.75, right? That's what typical situation is. Suppose that last summer, 65 of a random sample of 78 guests did get it. So you've just told me P hat is 65 out of 78. That's good news. And does this indicate that the proportion of guests that get a big fish is different from 75? Okay. So number of successes, there were 65 of them out of 78 guests who got a big fish. And their proportion should have been 75, right? That's what it would be normally. And we're trying to see, is it not equal to, and I'm going to generate results. And it's that number there. And what was the significance level? That's important. 5%. Uh-oh. At the 5% level, isn't that p-value too big? Right? So there's not statistical evidence that it's different than 0.75. Now I'm going to change something. Let's make it greater than and generate results. Isn't that p-value less than 5%, and so that it is significant? You see that? Which kind of takes me to the last talking point for today. And that is, you have to be very careful when you do hypothesis testing about choosing which direction to go, right? Less than, greater than, or not equal to. And you also have to be careful about which significance level you choose. Would you agree that if I chose that significance level, wouldn't I get many more successes than if I choose a 1%? Wouldn't there be lots more times where this is true when that is true? And did you notice in that last question, if I changed a not equal to a greater than, I got a success. When it was not equal to, it was too big, right? But when I changed it to that, it worked. So you have to be careful about what you're doing. Now, there is an unscrupulous group of people who will do the analysis first. That means they find the p-value. And then they mix and match what they want to make it work, right? So they'll start off saying, I'll do a not equals to at 1%. Ah, didn't work. I'll do a not equals at this. Still didn't work. I'll do a greater than at this. Gotcha. And that's the one that they use. And then they report, hey, I've proved something. So if you want to look out for people who are doing that, this cherry picking thing, the easiest way to do it is, can you imagine that they did 3 or 4 or 5 different things? If the p-value, if the significance level was 0.01, then the next time they did it was 0.10, and then the next time they did it is 0.01, and then the next time they did it is 0.05. Do you see what they're doing? Aren't they moving the goalposts to get success? Now, if they make it 10% all the time, or they made it 1% all the time, I'm much happier with that. But I am not happy with this, because basically what you're doing is you're looking at the answer before you make up your mind. And that's not the way you should be doing it. When you do these stories, you should actually be picking your alpha and this guy first. Okay, am I going to prove it's less than? Am I going to prove it's more than? Am I going to prove it's different, right? You've got to choose that. Am I going to live with a 1%, a 5%, or a 10%? You choose that. And once you've done that, then you actually should be going out and collecting the data. So you should actually be doing the data after you've made those commitments, not collecting the data, see what the numbers look like, and then play about with it to get a significance level. Can you imagine the temptation that is there to make people do it this way? Because you want evidence, right? You can't really do a report saying, well, I just spent $100,000 in 6 months in my life looking into this. And the answer was inconclusive. I didn't prove anything, right? Hard pill to swallow. But if you're being an honest scientist, that's what you need to do. You need to just say, some things just don't work out, and I'll look at something else.